Okay, this is lecture 13, the last lecture before our midterm examination. So up to now we have spent our lecture hours, 12 lecture hours for discussing the basic device physics, and now it's time to move to the PN junction. In the case of PN junction, where can you find the PN junctions? The answer is almost everywhere in the VLSI devices. So, but let me just give you more concrete example. So, let me just draw typical schematic. So here we have a gate, and here we have a source and drain, and yes, here we have the contact substrate. And in the case of N MOSFET, where electrons are moving charge carriers, in this case we introduce N++ region, so which has really high doping density, and N++ region in source and drain. So basically we have a lot of electrons and a lot of electrons which try to conduct. However, since we have introduced here certain p-type region, so without the assistance of the gate bias voltage, actually the conduction path between this source part and drain part is disconnected. So only when we apply sufficiently high gate voltage, then we can conduct, or we can connect both regions by certain inversion charge layer. Everybody in this room should understand this basic knowledge before enrolling this course. So therefore, when we have a certain gate bias voltage higher than so-called threshold voltage, then we can have the current, meaningful current value. So, but today's point is PN junction. Then where can you find the PN junction? So since the substrate is typically implemented with p-type substrate, so you can see that here and there exist PN junctions. So please think about this PN junction. This PN junction, yes, we have N plus and P, and my question is, which one shows higher density and which one shows lower doping density? Obviously this p-type density, so Na value is much lower than the value of donors in the N plus region. You know, in this case this is typically orders of 10 to the 20 per cubic centimeter, or even exceeding 10 to the minus 10 to the, not minus, 10 to the 21 per cubic centimeter. And in the case of this Na substrate doping, the typical value would be 10 to the 17 or 10 to the 18, much lower than that. So the typical thing we are looking at is, here we have really deep structure, and only on top of this deep structure here we have N++ region, which has a really high density. But actually physical depths of this physical depths of this N++ region is not that important in this case, because this is really highly doped. So that will be clear in our later discussion. So simply speaking, many PN junctions we can observe in the realistic devices are many cases one-sided junction. So one-sided junction means that their doping densities are not balanced. One doping polarity has much higher density than the other, so we can just think about, yes, the depletion only in one side. Anyway, so this is the case for our N MOSFET. Of course, if we consider the other type of MOSFET called as P MOSFET, then instead of this N++, then we just introduce P++, and doping level is more or less similar, and instead of this P-type substrate, we introduce N-type substrate. Also, doping density is more or less similar that of P-type density in the N MOSFET. So we can think about just one type, for example, N plus P junction. After that, we can just convert its polarity to P plus N junction without much difficulty. Okay, so are you with me? That is the typical thing we will have. And okay, so let me just wait for a while. Okay, so the main purpose of this PN junction is the isolation between different regions. So for example, in this case, of course, here and there they are separated by this PN junction. Everybody in this room understand, if we apply positive voltage to the P-type region, then this structure start to conduct the electric current. So here we have a P-type region, and here we have a N++. So if we apply the substrate voltage higher than, for example, source voltage or drain voltage, then what will happen? In this case, this PN junction or this PN junction is located in its forward bias mode. The PN junction located in its forward bias mode start to conduct, then we can observe the current flowing through in this direction, because this is positive and this is negative, and this is positive and negative. So if we have such kind of situation, then when you measure the current of this device, for example, let's say that you have here drain contact, and you just measure the value of current. However, if we have this kind of current component originated from the current between substrate and drain, then what happens? In this case, we have to say ID, drain current, is no longer equal to 0. So that means that we can have a certain current component between this substrate and source region or drain region. This is really undesirable phenomenon. So we don't want to have any kind of current conduction except for this conducting path. The current flowing through our inversion layer. This is the only desirable conduction path inside our MOSFET. All other current paths should be eliminated, and this is one of the most serious conduction path, leakage path in our transistor. So therefore we wanted to eliminate it. So understanding the current conduction mechanism in the p-n junction is so important, because by understanding the current conduction mechanism through this p-n junction, we can eliminate, at least try to eliminate or suppress this leakage current. But please note that I have just assumed one really strange case, like substrate voltage is higher than drain voltage or source voltage. In practice, that never happens. So since we apply higher voltage to the p-type region, this p-n junction is actually turned on. So this is not a desirable case. So what we wanted to have in usual case is just to keep it 0 or keep it lower than n plus region. Simply speaking, our p-n junction is located at its equilibrium state or in its reverse bias case. So let me just think about this one. If you apply, for example, V substrate equal to minus 2 volt, for example, and you apply 0 volt to your source and 1 volt to your drain. Please think about this configuration. Then what happens? Please try to the operation regime of this source substrate junction and drain substrate junction. In the case of this source substrate junction, your n-type region is biased with 0 volt and your p-type region is biased with minus 2, so therefore it is in its reverse mode. Even in the case of this drain to substrate junction, although your n-type region is biased with 1 volt, yes, you have negative minus 2 volt, so it is also in its reverse bias condition. So it is important to place or operate our p-n junctions in their reverse bias mode. Otherwise, if you just apply forward bias, then it will try to conduct, and it is directly related with this undesirable leakage current, and that should be suppressed at best. Okay, so now let's go to the p-n junction. So basic course always try to give you some feelings about how can we have just a built-in potential or built-in electric field inside this p-n junction. But I assume that all of you have already heard about built-in potential or built-in electric field, and I wanted to revisit this phenomena once again, description once again with a little bit more advanced description. Okay, so let me just think about qualitatively. So we must have built-in electric field inside this junction structure. Otherwise, there will be certain current conduction. That is the main message I wanted to tell you. So simply speaking, here we have p-type region, and here we have n-type region. So we have so many holes, and here we have so many electrons. So without any electric field, then these so many holes will try to diffuse over the junction and try to move to this n-type region, because how many holes are there? Actually no hole. How many holes are there? For example, here we have 10 to the 17 holes per cubic centimeter. So a lot of holes and almost no hole there within short distance. Then yes, it will strongly try to diffuse into that way. So please note that this is Hall flux. Of course, from the viewpoint of electron, the situation is the same. Since we have so many electrons and there is no electron at all, almost no electron at all, so we will have strong flux, diffusion flux into the p-type prism. So everybody in this room now understand there are two major conducting mechanisms in this course. What is it? One was the diffusion and one was the drift. And now we are saying that there exists a strong diffusion current for each carrier, Hall, electron. Both of them try to diffuse. Then the only way to keep or balance this strong diffusion current component is, what the remaining hope is only drift. Without this drift term, then there will be net charge current. Then maybe some of you can ask me this question: why we have to cancel out this diffusion term? Usually we wanted to use this p-n junction as an electronic device, so therefore current conduction is quite natural. However, please note that even in the case of our electronic device, at equilibrium, we have quite a strong restriction, like at equilibrium, we must have zero current density everywhere inside our device. So let's think about the p-n junction, and we just placed this device at its equilibrium case. Then, even though physical quantities changes at every position, however, the current density calculated inside the device should vanish everywhere. So simply speaking, at equilibrium, we must introduce the existence of drift term, which perfectly cancel out this strong diffusion term. Then who generate the drift term? The only way is, yes, the only way is the existence of electric field is needed. Otherwise, so our electrons will just diffuse and holes will diffuse. Then now think about the direction of electric field. Yes, hole try to diffuse over this direction, so therefore our electric field should push back our holes to the negative x direction. So electric field, in order to push our holes back into their original position, p-type region, then electric field should be headed in this way, because hole is positively charged. The direction of electric field is the same with the force experienced by our holes. In the case of our electrons try to move this negative direction. So therefore, in order to push them back, then we must push them toward positive direction. Then how can we push them back to the positive x direction? The way is our electric field should be also this negative direction. Because electrons are negatively charged, so if our electric field is headed in this negative x direction, then actually force will be converted into positive direction. So simply speaking, so with one single desirable direction of this electric field, we can push both carriers back toward their original direction. So instead of this simply speaking, in this case, we have to assume the electric field heading in this way. So now think about this one. If we have a certain electric field starting from this n-type region and ending at this p-type region, simply speaking, in order to generate such a kind of electric field, we should provide some sources of our electric field. And what is the source of electric field? Electric field is generated from the net charge density. Simply speaking, here we must have positive net charge density. So in order to generate this electric field, also we must introduce same amount of negatively charged densities in order to just finish the span of the electric field. Otherwise it will just propagate further. So we must balance this positively charged part and negatively charged part. So here we have a similar discussion here. How can we build an electric field inside our p-n junction? Of course, we must provide positively charged layer and negatively charged layer, and they should be perfectly balanced. So simply speaking, let's think about certain imbalance. Here we have 4 positively charged particles and just 3 negatively charged particles. Then what will happen? Then when we consider a system surrounded by this overall system here, then inside it the net charge density is no longer 0. We have net positively charged region. Then that means that actually we will have a certain outgoing flux, electric field out of this center part. It means that without balancing this charge density, then we will have a non-zero electric field far from that junction. Then what will happen if we have such kind of a charge imbalance at a short time? Then our charges, moving charges like electrons and holes, will be affected by that remaining electric field, and they will try to neutralize this electric field, and eventually we will have no electric field originated from this junction. So we will have the perfect balance between positively charged particles and negatively charged particles in a larger scale. However, if we introduce a certain resolution within this junction region, then of course there will be charge imbalance. Okay, so let me just come back. So then how can you build an electric field inside this p-type p-n junction? Then we need net charge density, because electric field, or similarly the displacement vector, is originated from our net charge density. So we must assume the existence of a non-zero net charge density inside our system, and from our discussion it is obvious that we must have positive one and negative one, and also perfectly balanced. So yes, then the next question is, then how can you obtain this positively charged layer in originally n-type doped region? So in originally n-type doped region, if we consider this part, actually we have in this region we have ND density of positively charged atomic cores, and the same number of ND density of our negatively charged mobile electrons. And now we wanted to have positively charged layer. How can we make a positively charged layer? Here, in homogeneous system, actually they are perfectly balanced. That's the reason why some of these two contributions cancel out each other. However, if we assume that this mobile carrier called as electron is removed from our the near junction part, yes, if we just eliminate or neglect this component, then remaining component is just the one from our doping density, and this doping density is originated from our atomic cores, and they never move, they just stay there, so they are called as immobile. They cannot move, they are just fixed there. So simply speaking, how can you provide positively charged particle near junction part? Actually, this mobile charge electrons are removed from this junction part, and the physical origin of these positively charged particles is they are just net ionized impurities. So we can have this kind of conclusion. Also, same discussion can be applied to this p-type reason. Yes, here originally if we have a p-type reason, then we will have Na density of negatively charged impurities, and also Na density of positively charged holes, but these holes are removed from this near junction part. Then now we can see just Na density of negatively charged impurities. We have spent quite a long time about the balance between these two charges. So please try to understand here the physical mechanism to provide this positively charged particle is just Nd, the doping density of n-type reason. And here we have the negatively charged layer, and how can we supply this negatively charged layer? It is done by our acceptor density. However, we must have the perfect balance between these two layers. So now think about this one. One is, for example, 10 to the 20 per cubic centimeter, and Na happen to be 10 to the 17 per cubic centimeter. 1,000 times difference in their doping densities. And let's assume that the thickness of these two layers are the same. Then what will happen? Although the thickness is the same, however, one part is 1,000 times highly populated, so charge balance cannot be obtained. In order to get the charge balance, what should we do? Actually, the distance between these distance, so from the metallurgical junction to the end of this depletion layer, should be approximately 1,000 times longer than that of this n-type reason. So let me just emphasize once again, stress it once again. Let's say here, let's call this distance as xp, so p-type depth, and let's call it as xn, and the depth of depletion layer in the n-type region. Then the relation between this xp and xn is quite obvious. Means that in order to have the perfect charge balance, Na A times xp should be equal to nd times xn. Otherwise, we will have the disobeying the charge balance. So we must have this condition. Okay, so I expect that all of you have already studied the p-n junction, so please just think about this as a quick review of p-n junction. Okay, so then let's go to another one. Now we should be able to draw the energy band diagram. So energy band diagram is a so important concept. We must be able to draw every time. So let me just consider basic rule to draw energy band diagram. So first of all, let's assume the equilibrium. Yes, we are now considering the equilibrium. That is not that surprising. At summer equilibrium, Fermi level can be defined, and usually we set this Fermi level as 0 electric volt. So Fermi level at equilibrium becomes the reference energy level. So then maybe you can ask me this question, but actual case we have to consider is not in the equilibrium case. Usually we must consider non-equilibrium case. Yes, you are right. However, before drawing your band diagram for general cases, please try to always draw the equilibrium band diagram. Once starting from the equilibrium band diagram, then later you can think about additional effect by applying additional terminal voltages. So please, at equilibrium, now we can define Fermi level, and that is the strict reference value for our energy levels. And our rule is, okay, there exists an interesting structure called as a p-n junction. However, away from that junction, nobody can catch there exists p-n junction. That is the point. Yes, there happens something, wow, quite interesting and quite active. However, that really happens near junction region. Away from that junction, or even close to the position called as terminal, anode terminal or cathode terminal, then our system is quite close to its local equilibrium case. That is the assumption we will have. So are you with me? It means that here we have, let's say that there are two countries, they are fighting each other. However, let's say that there is a certain rural country here, rural village. Then although there is a significant conflict between these two countries, but I never heard about the war. What happens? This everyday life is just the same as before. So just like p-n junction here, we have a p-n junction, and the electric field or electron density, physical quantities rapidly changing in this part. Yes, in this part everything changes so steeply. However, if we are located in this position, then our electron density and hole density is never affected by the existence of p-n junction located far away from our observation point. So simply speaking, if we have a p-type region here and n-type region here, then beyond a certain range, yes, how long is it? We have no idea. However, let's assume that there exists a certain finite extent of affected by this p-n junction. Beyond that level, we are now assuming that the system is in its local equilibrium. What is local equilibrium? Your electron density just follows the donor density when you have n-type reason. Your hole density follows the acceptor density when you have p-type reason. Simply speaking, since we have a p-type reason here, then our hole density is quite close to the acceptor density, and our minority carrier density will be quite close to Ni square divided by our another acceptor density. Same happens in this part. Yes, hole electron density is quite close to Nd, and hole density is quite close to this form from the mass action rule. So yes, in this case, in order to have electron density or hole density in this way, our Fermi level should be located. In order to have more holes, then our Fermi level should be close to valence band. Otherwise, we will not have many holes. If our Fermi level is located here, yes, then we will have more electrons and less holes. Yes. So since this part, this region is the p-type doped region, then it is obvious that the distance between Fermi level and valence band will be much shorter than distance between this conduction band to Fermi level distance. So we can assume this kind of a short closeness between Fermi level and valence band. Then, since Fermi level is the reference, then from this discussion now we can understand, since Fermi level, since this is the reference, where can we find our valence band? Then we can place our valence band in order to keep our hole density as Na value. So please note that this is the reference. Valence band is not the reference. Valence band is adjusted to keep our hole density as acceptor doping density. Similar thing can happen for our equilibrium n-type region. Yes, here we have a reference Fermi level set as zero electron volt. Then we have a closed conduction band H in order to keep our electron density close to doping density. So point is, we have completely no idea about what happens in this central part called as junction. Right now we have no idea. The only thing we know is there are separated layer of positively charged particles and negatively charged particles. So maybe there will be certain electric field in a short distance. However, except for that, what is the form of our conduction band in between? For example, is it located in this way, or is it located in that way, or that way, or that way? Right now, we don't have any idea about their shape. But even though we have no idea about their behavior in between, but at least only from these approximations or these assumptions, then we can now understand from the viewpoint of our conduction band electrons located here. The p-type is seen as less attractive part. Okay, so always since this energy is the energy seen by our electrons, so therefore they wanted to keep the lower energy region. So if we pick up one electron and ask it, so where do you want to stay? If you can choose, then obviously, since this is more lowly energetically placed, so electrons will try to first to occupy this part, and with less probability or lower probability, it will occupy this highly doped region. So although we have no idea about the internal behavior between p-type region and n-type region, then we can understand there will be so many electrons, and since this is energy seen by our electrons, energy seen by our holes is actually should be inverted. So where can you find more preferable position for our holes? Yes, to them actually this position is more probable or more preferred position, because to holes actually we have to, in our mind, we have to invert this energy band diagram, and this is relatively low energy part, and this is a high energy part for our holes. Okay, so that is the situation, and although we have no idea the exact form, but we can think about the energy barrier between these two parts. So simply speaking, the energy barrier shown here is obtained from the doping density. Actually, this distance is obtained from your NA value, and this distance is also obtained from your ND value. So from these two doping densities, actually the position of your conduction bands are already given, and their difference determines the energy barrier seen by our electrons. So if we, by applying something, if we can reduce the energy barrier, for example in this way, then more electrons will overcome this energy barrier and jump into or move into this p-type region. On the other hand, if we can by some way raise the barrier, if we can make an even higher barrier, then movement of our electrons will be even further suppressed from this direction. Okay? So are you all with me? Okay. So yes. So now you understand there exists the difference in their potential, and potential, conduction band or valence band, they can be easily converted into the intrinsic Fermi level, and intrinsic Fermi level is directly related to what? To the electrostatic potential. Please try to remember the relation between your intrinsic Fermi level and the electrostatic potential. So electrostatic potential is just pointing out the intrinsic Fermi level of our reference material. So now we can understand also potential will show certain variation in between these two regions, p-type region and n-type region. Now assume that so donor density in the n-type region and acceptor density in the p-type region are given as ND and NA respectively. We have already used this form several times. And then now in the n-type boundary condition, in n-type boundary, then we can think that this is the expression for our potential. Please note that this is so-called summer voltage. So since the Professor Tower's book doesn't introduce any specific symbol for this summer voltage in this semester, I will try to write it down in its full form, kVt divided by Q, but they are in many cases written as, once again, summer voltage Vt or VTH, something like that. But in order to eliminate confusion between threshold voltage, I will try to keep this symbol as exact as possible. And you know, here we have a summer voltage, and that is obviously positive number. So please try to remember the value of summer voltage at 300 Kelvin. What was the value? You must remember the value 25.85 millivolt. At least you must remember the value at 300 Kelvin. And you know, this is a positive number, and here you have a natural logarithm, and this is the argument is nd divided by ni. nd is much higher than ni, so therefore argument of natural logarithmic is the value much higher than number 1. So you know, this one is a positive number, and of course this is also positive number. So what you can see is, okay, this is always positive. Simply speaking, since n-type reason is n-type reason, so you know you have more electrons than holes, so you have a positive sign for your potential. Following the same procedure, in the case of a p-type reason, you can find that your phi is given as this form depending on the doping density, and also it has negative sign. Where can you find the negative sign? Yes, here you have negative sign. If your accept density becomes higher and higher, then actually your natural logarithm, it has higher value, larger value. However, since you have a minus sign, so you have a negative value, and their difference, that is given as the built-in potential. So the difference between this one, n-type potential, and p-type potential is written in here. That is built-in potential, and it really depends on your doping densities. Do you have any question? So simply speaking, once you set the doping densities, yes, this is 10 to the 20 and another part is 10 to the 17, then now you know the value of built-in potential between your p-n junction. So please let me know if you have any question. I'm just giving you this lecture for your quick review, because you know all of you have already attended the previous course for semiconductor device physics and semiconductor device, and the understanding the p-n junction was the most important lecture content in that lecture. So now let me introduce the depletion approximation. As we will see later, depletion approximation is not an exact one, however really good approximation. So in this depletion approximation, we assume that there exists certain sudden boundary or sudden abrupt change of electron density. For example, we assume a certain range xp. Within this xp, actually there is no hole. Holes are completely eliminated. And another one is, beyond that level or beyond that position, our holes are completely recovered. So what is the assumed hole density? That is actually just NA. So in this part, since we have the perfect balance between acceptor density and hole density, actually this is just regarded as perfectly neutral. There are negatively charged called as ionized donors and positively charged particles called as holes, but their density are the same. So in this part, this is completely neutral. And in this depletion region, since there is no hole at all, therefore this part is negatively charged due to the remaining ionized acceptors. Same discussion can be applied to this n-type region, since all electrons are completely removed following the depletion approximation. Then in this case we have just positively charged layer. Beyond that position, beyond that point, then we have once again neutral region. Then now from the viewpoint of net charge density, net charge density low, then our net charge density can be simplified quite significantly. Actually, we must consider low net charge density as a function of position. However, by adopting this depletion approximation, we can just consider piecewise constant behavior. So, if x is even lower than minus xp here, then net charge density is just 0. And if x is larger than xn, for example this point, then once again net charge density is 0. And if we have the condition like although larger than minus xp, however belonging to the p-type region, then net charge density will be just minus q times na, acceptor 1. And if we have the n-type region and in its depletion region, then we will have a low equal to positive q times donor density. So simply speaking, by adopting the depletion approximation, we can just make a great simplification of net charge density. That is the key point we wanted to make it available to us. Of course, it has serious problem because we are now talking about the electrostatic potential and net charge density. Electrostatic potential and net charge density are connected through the this way. If we know net charge density, then we can calculate the potential by solving the Poisson equation. We will do it today. However, there is the other direction. If you have the potential, then you can also construct this net charge density. How can you do that? At equilibrium, please try to remember. Your net charge density is simply given by positive q times p, contribution from your holes, and minus q times n, contribution from your electrons, and all other like your donor density and acceptor density, position dependent quantities. And please remember once again, your hole density and electron density can be written as a function of electrostatic potential by adopting intrinsic carrier density exponential phi over kBT over Q. Yes, you know it. And also in the case of hole density, that is given by Ni times exponential minus phi over summer voltage. So can you see it clearly? So I just written Ni times exponential minus phi divided by summer voltage. So simply speaking, they are connected in two ways. So what we have done in this depletion approximation is just to neglect this interaction. Yes, we neglect this interaction and we just say that rho is given as this form. Then natural question is why rho is given as this form? That is the beauty of this approximation. So by insight, we just say that, well, although there is no exact supporting material, but the net charge density will follow this form. Yes, then we can generate the electrostatic potential out of it. Okay, please understand. It is our choice to take any kind of approximation. However, whether that is valid or not is obtained from the result of that approximation. When you make a certain approximation and your approximation gives you quite close result compared to the numerical simulation result, then your approximation was good. But let's assume that you make a seemingly very good approximation to your model derivation and your result seems to be quite awful when compared with the realistic numerical values. Then what happens? Although seemingly looks quite reasonable, but it was not that good actually. So please note that the validity of any kind of approximation should be tested against the real result obtained from that approximation. But everybody understand depletion approximation is quite good. So one of the best one we can see. So now since your net charge density is so simple, so in neutralism there is no charge, and now we have constant value of a negatively charged particle and positively charged particle. After that it's over. Yes, here we have still rho equal to 0. Then starting from this position, then you can integrate it. So simply speaking, you can do it. So I will just give it to you. So since rho is position dependent, for example, if we have a p-type region, then we will have this net charge density, and if we have an n-type region, then actually we will have this net charge density and negative sign. Also, this is actually minus times q epsilon minus na, because we have a negatively charged layer in the p-type region. Although I have not explicitly written in this slide, but here we have certain range like x is even lower than minus xp, or x is larger than xn. In these cases, actually our equation simply should be the form like this. Second derivative of our electrostatic potential should vanish. Yes, and now we assume this kind of thing. Yes, there is minus xp, the end of our depletion region, and let's say that here we have xn, the edge of our depletion region, and now let's say that here we have a non-zero electric field. and let's assume that at this point we have a non-zero electric field. Then what will happen? And now here we have a neutral, and here we have neutral. Simply speaking, if we have non-zero electric field, and if this is really neutral, then we cannot change the electric field in this region. So please try to understand what is the Poisson equation. Simply speaking, the gradient of electric field is related with net charge density. Therefore, if we have a perfectly neutral region, then we have no knob to change the electric field. So simply speaking, if we assume these two cases, yes, this part is neutral and we have a non-zero electric field, it means that even when we go too far away from the depletion region, then we will have exactly the same electric field at that point. That never happens. So although junction is located far away, I can feel that electric field. That never happens. If I feel the electric field, then my colleagues, like so many electrons, will push there, rush into there to neutralize it, and eventually I will not feel any kind of electric field. So simply speaking, in this neutral region, we must have zero electric field. So simply speaking here, assuming vanishing electric fields at minus xp and positive xn, these conditions are obtained from the natural physical consideration. Otherwise, if we expect any kind of non-zero electric field, then that introduces quite a strange thing, strange behavior, like we can feel the electric field far from the junction. Okay, so now if we assume this kind of thing, now I think that many kind of equations, they are summarized, then please try to understand this one. So now we can understand this way. Previously I have drawn the net charge density law. However, by integrating this Poisson equation only once, then we can find the electric field. So please note that our Poisson equation is simply given by this form, law. Therefore, by integrating our Poisson equation once, so dE over dx over dx equal to minus rho epsilon dx, then we can calculate the electric field at our from A to B, then B minus A can be calculated. A is lower point, lower limit, and B is upper limit of integration. So by doing this kind of thing, we can easily calculate the electric field profile shown here. So however, since this is electric field, and electric field is nothing but just first derivative of our electrostatic potential, by integrating it once again, then what will happen? Then we will get the potential difference between these 2 points. For example, let me just perform the integration of electric field starting from here and ending at this point. By integrating this electric field along x direction, then we can get the potential difference between these two boundary values. So, Then what is the result of this integration? It is quite obvious that the area is corresponding to the result of integration, and this area is simply given by half times xn plus xp times minus maximum electric field. This is the maximum electric field we have calculated in our previous slide. So simply speaking, this is the integration of electric field, and it is equal to what? The potential difference between p-type region and n-type region. And we introduce a certain symbols, built-in potential difference in our course. Therefore, we have this kind of expression. Okay. Our usual way of model derivation is now try to find out this WD. We assume that since we know the doping densities of both p-type region and n-type region, usually this built-in potential is given number, and the remaining is when the given doping densities are understood, then how can we obtain this ND? However, here we have also maximum electric field, so therefore we have to find out certain relation between maximum electric field and depletion width, and that is shown here. You can easily check it. So maximum electric field can be written as in terms of WD. Therefore, by introducing this relation, then you can obtain the depletion width in terms of your built-in potential and doping densities. Na and Nd, they are doping densities. Please note that actually this built-in potential also a function of Nd and Na. So when you change Nd and Na, explicitly you have changed values Na, Nd, Na, Nd, and implicitly also your phi Bi built-in potential is affected by this doping changing. Point is, although written in this form, but you can now understand a little bit better when you have a look at this form. 2 epsilon q, yes, this guy, this guy, this guy, and now let's just consider the doping dependent term. Then how can you summarize it? This is Na divided by Na Nd. Then it becomes just 1 over Nd. And the second term, this Nd term, is divided by Na Nd. Yes, it is nothing but just the inverse Na and phi Bi. So simply speaking, now introduce more realistic values like Nd equal to 10 to the 20 per cubic centimeter and Na equal to 10 to the 17 per cubic centimeter. Then who decide this term? If you have, for example here, Nd equal to 10 to the 20 and Na equal to 10 to the 17, then since this Nd term is 1000 times larger than Na term, actually it does not contribute. The only contribution can be obtained from the one which is originated from lowly doped music. So simply speaking, if you have on a one-side junction, for example, you can have N plus P junction, then which one decide the depletion width? Actually, p-type doping density determines the depletion width. And if you have, for example, P plus N junction, which can be easily found in your P MOSFET, then actually your N-type doping density, donor density, will determine the depletion width. So in the case of this P plus N junction, so which one determines the depletion width? Actually, ND will make it. And also, where can you, when we make a comparison between XN and XP, which one will be longer and which one will be shorter? Of course, and XN, the depletion width inside this N-type region will be much longer than our P-type region. Finally, I wanted to ask you one more thing. In this case, what is the potential difference applied to your P-type region and N-type region? Even in this case, most of our built-in potential is only applied to your N-type region. Because, let me just come back to this one. In this case, in order to give you some good feeling about or understanding, I have just drawn the balanced p-n junction. More or less, p-type and n-type region have similar doping density. Then please try to the potential difference applied to the p-type region and n-type region. This is p-type and this is n-type, and the area of this part is corresponding to the voltage difference applied to your p-type region, and the area of this region that is corresponding to the n-type region. So think about, for example, p plus n junction. Then how can you draw your electric field? This graph looks good because this is more or less a balanced one. But now let's assume that P plus N1, for example, 1000 times higher doping density for P-type region. Then you can see that actually most of your depletion region will be consumed by your n-type region, and there you will have an extremely short distance for your p-type region. Then when you draw electric field, then that will be the shape of your electric field. After that, the area assigned to your p-type region is much smaller than the area assigned for your n-type region. So simply speaking, the answer is quite simple. In reality, the p-n junctions are almost always one-sided. One part has much higher doping density than the other, and all kinds of properties are just determined by the property of lowly doped region. So if you have M MOSFET and this is M plus NP, then who decides the property? Yes, this guy determines your junction property. Okay, please understand this one. Yes, then I think that we have covered here, and I think that this is the last slide. Please have the number 10 to the 20 doping density and 10 to the 17. 17 is quite a reasonable number for substrate, and in this case depletion width is roughly speaking just 100 nanometer. So it means that if you introduce, for example, 10 times higher doping density, 10 to the 18, then what will happen? Your depletion width will be reduced approximately 3 times. So are you with me? So because lowly doped region determines the depletion width, and since it is 10 times higher, so our calculation should be related with square root of 0.1. So it is roughly just multiply 1/3. Yes. So then let me ask you the final question. Instead of this changing this one, 10 to the 17, I just change our donor density like this. Acceptor density is just kept as 10 to the 17, but instead of that, ND is increased by factor of 10. What will happen to our depletion layer width? That doesn't introduce much difference, because yes, 1 over ND was already quite small. Even 10 times the higher value doesn't make any change. The only thing we can consider is now our built-in potential will be increased a little bit. So how much? So that will be delta built-in potential will be just kBT over Q times log 10. You will have slight increase of your built-in potential, and that will introduce a slight change in your depletion width. Are you with me? Okay, so I think that this is the last lecture before our midterm examination. As I told you before, so from now on I will think about how can I give you some midterm examination problems, but I can certainly say that there is not that much calculation required for your midterm examination. In this course, we have spent most of our time for getting some concepts on important lecture materials. So please try to understand the lecture contents instead of doing many calculation. Of course, calculation is really important. However, the main purpose of my lecture in this semester is not giving you the calculation technique. So, okay, then if you have any questions, then please join our tomorrow's online office hour. Thank you.